Time to talk about languages. One of the things, the great technologies, is you have to be able to build your own language when you need it. Okay, and this is stuff that I've taught for many years. This stuff, the second half of this today, is stuff I've taught many years to freshmen. Okay, so this is not something you should be worried about. But it's a very striking phenomenon. How do you build the universal machine very simply? Okay? Now, every language I know of, with the exception of Prolog, is basically an eval-apply interpreter.
On that side.
Okay? Who's that?
What's going on?
Somebody?
Boulder, Colorado, what's up?
The Colorado, who is it? Okay, well, I'll assume it was an accident there. So what I'm going to show you right now is the essence of an interpreter for a language that you can write, which basically allows you to make whatever language you want. Okay? So here it is. This is the first page of it. It's written in abstract syntax. Person with a telephone. How he can stand that, I don't know, but that's telephones.
Everyone here has a phone except for you, Gerald.
Yes, you're right. Okay, so this is an abstract syntax interpreter, and it turns out that it's written in its own language very easily. So what we have here is a procedure that takes two arguments. The arguments are an expression to be evaluated and an environment in which it's to be evaluated. What it means to be an environment is that it is the mapping of symbol value names to values. Okay, now of course this could have been written, this conditional could have been written as a generic operation, and it will be. It's only just easier to see it on the screen right now in one piece if written here like this. So we have a self-evaluating expression. That's an expression that's something like 1 is a self-evaluating expression. Okay? Or 3.5 is a self-evaluating expression. Or the string high is a self-evaluating expression. Things like that. And if the expression is self-evaluating, then it's the expression itself. What if I have a variable like maybe x, or exp, or env, or plus? Okay, those are other kinds of names, variables. Okay? Indeed, the addition operation is just attached to the symbol plus as being its value in something like a Lisp. Okay, so if I have a variable, then I better look up the variable's value in the environment. That's all I do. Now, there's this thing about quotation. Quote foo. Okay? Quotation's a very interesting thing. There's a great history to it. Say your name.
Seno.
Say your name.
My name is Seno. S-E-N-O.
No, say your name.
Oh, name.
Okay, good. Okay. That's what quotation's about. Okay? So, say your name is one statement. Say your name is a different one. Okay? And they have different meaning. And in order to distinguish those two meanings, we have quotations. This has caused some serious trouble in the history of philosophy. Turns out that quotation produces opaque contexts, which means you can't substitute equals for equals in a quoted context. So for example, John knows that the morning star is Venus. The morning star is the evening star. We can't deduce that John knows the evening star is Venus. Okay, that's a problem. That's a quotation problem. Although I used the that to specify a clause that would have been quoted. John knows, quote, the morning star is Venus. There's assignment in some languages. Some don't. People don't like it. Haskell people would get mad. That's all right. That's their problem. Sometimes you need it, you know. Tough. Okay, so sometimes you have to assign a variable, which is in the environment. Okay, and assignments in Scheme look like this. To 32. Okay, and from then on, x is 32. There are definitions like this one. This one is defining eval to be a procedure of two arguments. That's really written as define eval to be a procedure, lambda of n exponent n, which is some stuff. Okay, so that's what that is. And there's a thing, a handler for that. That's all this is. These are the handlers that you're seeing here. Okay? If expressions have to be handled, conditionals, of which kind is a big complicated nest of ifs, it turns out. And we'll have to fix some way to do that. Lambda expressions are interesting. Okay? A procedure. A procedure is a thing which takes some arguments, has an expression or expressions inside it that do things, and those expressions have names inside them. Some of those names are defined in the arguments to the procedure, the formal parameters. But some of them are not. Some of them are free variables. Okay, so where do the free variables get their meaning? They get their meaning from some environment. We can make choices about where we get them from. The best choice, the one that I like, is the lexical environment, and that's what this is. So given a lambda expression, I make a procedure, which is the lambda parameters and the lambda body. So I'm making a new object, which combines together the parameters, that's the names, the body, which is the program that gets run, okay, and the environment, which has the meanings of the variables in the lambda body that are not the parameters. Now, it turns out that, of course, this could be a very complicated compiler. I don't really even care. Or it could be that we've compiled this stuff. Lambda body could be a compiler, right? You know, that's a thing that produces something which could do the job, and we will. Oh, thank you. Okay? Yes, our computer's hateful. We've got to really fix this kind of thing. So then there's.
I'm not allowed to fix that one.
I see. Okay. Begin. I can do a bunch of things and return the last value. Okay, and that's what that is. So there are sequences of actions. Cond is a thing which is going to turn into a nest of ifs. I'm not going to worry about that. And application is the other interesting thing. How do you actually evaluate a composition of things that looks like this? For example, I've got the sum of the square of 3 and 4. Okay? Well, how do I evaluate? That's an application. It's got an operator and it's got some operands. Okay? Well, what we're going to do is we have to figure out what the operator is, first of all. What's that plus? Oh, we better look it up. But I don't really care. It could be a complicated thing. This could be the car. No, I'll make something horrible here. If greater than, I need an eraser. Okay, here. Okay. Okay. So this could be if greater than x3, then I want plus. Otherwise, I want minus applied to 4 and 5. Okay, and that's a perfectly legitimate situation. So I want to make sure that says if x is greater than 3, I want to add these two numbers. Otherwise, I want to subtract them. Okay, so I better have a way of evaluating the operator with respect to the environment. And then I have to get the list of all the values of the operands with respect to the environment, and then I have to apply the operator, the resulting procedure for which is the handler for that operator to those operands, to those arguments. Okay, so that's the first stage of a universal evaluator. Notice that this says nothing about the syntax. Really, I mean the fact is that this could be Python. That would be easy, okay? It'd be a pain in the butt, but it would be easy. It would mean that I have to define things like the text of the quotation, look up the variable question. All these things have to be defined, okay? The things that access the syntax. It could be hard to make it.
Well, you'd probably parse it first and then use the parse.
You probably would. I mean, I can imagine. Normally, what you do is you convert it to Lisp, okay? By part, yes.
That's the parse tree.
That's right, the parse tree. Exactly. You know, but I can't imagine doing this for, say, Perl.
Oh, no.
That would be horrifying or scary. Okay, so there are certain scary ones. Okay. Now, what's the other half of this? It's apply. Okay? And so what apply does is it takes a procedure and applies it to arguments. These are now real objects, real things that have meaning, as opposed to an expression does not have a meaning without an environment that describes the meanings of the variables in it. But a procedure is a closed object. It has meaning. And the arguments have already been evaluated here, so it has meaning. So what do we do? Well, if the procedure is a primitive, like maybe addition, okay, then some magic happens. But supposing it's not. Supposing it's a compound procedure. Well, the compound procedure has a procedure body, and it has an environment built in. Okay, and what we have to do is we have to extend the environment to be the result of pairing up the procedure parameters of the procedure with the arguments that were supplied over here, so that each parameter is associated with an argument. Okay, and do that in the context of the environment the procedure was itself defined in, which was passed in as part of the procedure. If you go over here, we made the procedure. Okay, we did over here when we made a procedure, we picked out the environment that the procedure was defined in. Okay, that's its definition environment. Here is it being used. Right. So we build up that, making a new environment, which is the old environment with these new parameter names associated with the argument values. Okay? And then we evaluate the body of the procedure in that environment, and that's all. Okay? So that's the basic structure of this. Now there are some details. How do you do a list of values? Because we needed that, right? We needed that here. We needed that over here. Okay? And we need how various handlers work. But list of values is pretty simple. List of values says I've got a bunch of expressions in an environment. If there are no more operands left, then I just produce something empty, an empty object. Otherwise, oh, and now I'm talking Lisp. See, I've just suddenly have specialized this to have, in fact, that's not a reasonable thing to have done. I apologize. I should use an abstract constructor. Okay? But this is easier for me because I pulled it out of a book I wrote a while ago. Okay? But basically, this is the thing that says, make a pair of two things. Okay? So I'm going to pair up the result of a value in the first argument operand with the list of values of the rest of the operands. So this is a little recursive procedure which produces a list of arguments. It could have been some other more abstract argument list object, which might be more appropriate if I were, but that has nothing to do with, again, the language I'm interpreting. That's in the runtime environment of the interpreter. So at least that does not constrain the language I'm interpreting. Okay? What does if do? If says if the predicate, an if contains three parts. If a predicate, a consequent, and an alternative. If the predicate is true, I want the consequent, otherwise the alternative. Well, if is defined in terms of if, of course. Okay? Why this works is very interesting. We'll talk about that in a few minutes, and why you can define things in terms of themselves. And it's a very interesting question. But if the predicate's value is true in the environment given, then the consequent should be evaluated. Otherwise, I should evaluate the alternative. That's all you're seeing. Then there's sequence of expressions. To evaluate a sequence, if I've got the last expression, evaluate it. Otherwise, evaluate the first one, and when I'm done with that, evaluate the rest of them. Okay? That's an ordering. And there are a few other little things. How do you evaluate an assignment? Well, there's a magic procedure for manipulating the representations of environments, which sets variable values. There's one for definitions that does the same thing, which adds new variables that weren't there. Okay, that's the difference. And whoops, that's it. Okay, so what you've now seen is the whole thing. This is a universal machine, and it's rather beautiful. I want to make some comments about it first of all. Okay, first of all, there's a mysticism associated with it, which I am pleased to be a part of. Apply. I hope you enjoy that. But if you don't like mysticism, that's irrelevant. The more interesting question is, what is this defined at all? I mean, after all, I've used the language and defined the language in terms of the language. And it's perfectly plausible for me to have made all those abstract syntax definitions be the ones for Lisp. For example, operator would be car, and operands is cooter in Lisp. Okay, and that's just an assignment of those things. That's why Lisp is so easy to work with, is because it's a very simple representation of a program as data. One of the reasons why people like me like it so much, because it's easy to write programs and manipulate programs and write programs and do all sorts of things with them. Okay, but that's not the essence of the matter here. Okay, but you see, there's really this other question of what it means to define anything at all. So, of course, you know that x plus y equals 3. I'm going to specify that. X minus y equal 4. This could be written as x equal 3 minus y, colon equal if you like, and y equals x minus 4. Right? Did I do that right? Okay. This is saying x and y are defined in terms of x and y. Okay? But we know it produces a sensible answer. All right, this has got a unique answer. There is a unique value for x and y. This is unique. However, x plus y equals 73. These two have no answer. This is a contradiction. Okay? Or, for example, a different group, 2x minus 2y equal 8. These two have an infinite number of answers. So actually, you can't tell by the shape of an expression whether it defines something. I want to be very careful about that. That they taught you in elementary school about you can't define something in terms of itself is nonsense. You can sometimes, but not always. Okay? What it means to get an answer, it depends upon the details. In this case, the coefficients of the linear equations. Okay, whether there's a unique answer. So what are these objects? These objects are equations. Okay, that's already interesting. That is, each of these, if you want to think about these, like this is an equation that says eval equals the lambda of 2 arguments, which is this big expression. Okay, and there is there's a few of these equations, some of which depend upon undefined symbols like plus. They happen to be there. I mean, I didn't tell what they were. Okay, but some of them are the things of interest, like x and y, eval and apply. Okay, and indeed, for some details, sometimes it means something and sometimes it doesn't. There's a lot of work on this. People have done the question of when, in fact, a set of recursive programs has meaning was I suppose, figured out finally by, I just lost his name, the guy from CMU, who used to be in England. Church and Strachey? No, not Church. Strachey and, Mumble and Strachey. Scott, thank you. Well, that's right, Scott. Thank you. I lost it. Every so often, the few brain cells go away, and what can you do? Okay, Scott. So they figured out when lambda calculus expression, which is what these are, has a meaning. Okay? I'm not going to try to elaborate on that very much, but it's a powerful and complicated set of theorems involving basically the idea that there is a limit in the limiting limit for in a interesting kind of topological space called a continuous lattice. And I don't want to get into that right now, but I'll give you a little feeling for the idea. Okay? So let's take something simple. How about the famous factorial procedure? Okay? What's factorial? Factorial is that procedure of one argument n, which is if equal n 0, the result is 1. Otherwise, it's the product of n and factorial of n minus 1. Okay? So there's a factorial procedure. Now, why does this have any meaning at all? Well, we can certainly say that there is a procedure which does nothing, which is just an error. And traditionally, that's got the name bottom. Okay? That's an error. And indeed, let's call factorial 0 equal bottom. Okay? Factorial 1, this is just factorial number 1. This is, let's call it sub-0, sub-1, is the following. It's that procedure of one argument, n, which is if equal n 0, the result is 1. Otherwise, it's bottom applied to minus n1. Okay? This is a procedure which is a good factorial procedure only if you're only going to apply it to one argument, one particular value of the argument 0. It always answers the right answer if n is 0, and otherwise it blows up. Okay? Well, now, how about factorial sub 2? Sub 2. That's the procedure of one argument n, which is if equal n 0, the result is 1. Otherwise, it's factorial sub 1 applied to minus n1.
Change the bottom on the previous line of fact.
I know, it'll be more clear. Thank you. Fact 0. Sub 0. Oh, you're right. Ooh. Thank you. I'm just being flaky. Sorry. Times n fact 0 of minus n1, fact 0 times lambda times n fact 1 of minus n1. Okay? So this procedure works for factorial of 0 and factorial of 1, but for no other values. Okay? And fact 3 is the procedure of one argument n, which is if n 0, the result is 1. Otherwise, the product of fact 2 and minus n1. And this one works for...
How would you load the bugs? I think everyone gets it.
Do I have any bugs? Top times n. Right. Okay. So this is saying that I have a sequence of factorial procedures, each of which is better than the previous one in that it covers a wider range. Okay? And the fact that there's a factorial n, factorial is the limit as n goes to infinity of fact sub n. Okay? So that's the idea that the Scott-Strachey semantics incorporates. Now, it's going to be a little more fun here because I love doing this. For those of you who haven't seen this sort of thing, for those of you who like this sort of thing, this is the sort of thing you like. I've just quoted, actually, that's Abraham Lincoln has been quoted a lot recently. Okay, okay. So, you see, what I can now write is a more interesting procedure. That procedure of one argument f, which is that procedure of one argument n, which is if equal n 0, the result is 1, otherwise times n f of minus n 1. Okay? We'll call this capital K or something. Okay? This is an interesting procedure because notice that if it's the case that I had real factorial, if I knew the real factorial, supposing I had factorial, then K of factorial equals factorial. Okay? So the real factorial is the fixed point of the operator K. Okay? Well, I'm not going to introduce Y operators here, but for those of you who would like to hear about this, you can bug me about it later. I love writing these on blackboards. I've done this many times in life. That I can show you, I can actually write the procedure called Y, which has the property that Y of F is F of Y of F. Okay? That is, Y of any operator of this kind is its fixed point, if it has one. Is a fixed point, excuse me, and we would like the least fixed point, but that's a different problem. Okay, so that's the why these things may actually mean something. That is, sometimes it's the case that you have these equations, these what are called recursion equations, and that they actually define something. And so here we have a combination of them, which is eval and apply and all of its favorite friends here, that in some sense either defines the empty language, the thing that doesn't work at all, okay, or some language, or it also defines, one of the things it defines is Lisp. That's one of the solutions of the set of equations, is the Lisp that we've been using, okay? Because that correct Lisp, if substituted, will produce Lisp back. Okay, that's the idea. And in fact, we are substituting it because we're running it. We run the metacircular evaluator you just saw in a correct Lisp. Okay. More slowly, yes. Okay. So that's some of the magic of building languages. Because all you have to do, of course, is produce whatever syntax the rules you want. And of course, you can add more handlers and more types of expressions. And you can add more types of procedures. And indeed, therefore, I really want to show you how I would do this if I were doing this in serious world, which looks like this. Okay? And we're going to be doing a lot of things that depend upon generics, because the real stuff has to be generic for it to be very good. Okay? So what we have here is the default evaluator. Okay? Okay, and the default, that's a handler if I have nothing else I want to do. Okay, it takes an expression and an environment. If the expression is an application, that's the last thing, then it does the thing you saw. Apply of a value, the operator in the environment with respect to the operands of the expression in the environment. I've been careful not to take a list of values here because I want to be able to extend this to be normal order as well as equilibrative order. That is, I want to be able to call by name as well as call by value, or call by need, or whatever the hell I want. Okay, this is going to be so general that I can do anything I please. And as a consequence, it's going to run even slower. But that's a different problem. Okay? Okay, but good compilers help. Okay? And then, so eval is a generic operator with default eval as the default eval. No question. Then there's a handler for lambda. Lambda expressions, No, sorry, sorry, for self-valuing expressions, the handler of eval for self-valuing expressions is the thing which takes the expression environment and returns the expression. The handler for variables is just the thing that looks up variable values. Takes two arguments, so I don't have to say anything there. The handler for quoted expressions is the thing that pulls the text of the quoted expression out. Okay? And indeed, well, we got all the rest. Here's how I make. Now I'm going to be careful. I'm going to separate out strict compound procedures. Okay, that's the ones that evaluate all their arguments, call by value. Okay, so if lambda expressions are going to be the ones that are strict compound procedures, because I'm going to have non-strict ones as well. Okay, that's ones that maybe defer their arguments. Okay. Handler for if expressions is the standard one you saw. Okay. Handler for definitions is the same thing you've seen. It's very simple. And a handler for what's the next thing here? Assignments, conditionals, all the ones you saw. Nothing very exciting here. But we get to apply. Apply is interesting also. This apply is going to take three arguments. And that's because I want to be able to defer evaluation. Sometimes I want to be able to make what we call, in the algol world or something in the scheme world, something called a thunk. A thunk being why do they call it that? Does anybody know? There's some mythology about that, and I can't remember what it was. Yes?
Pushing on the algol stack.
You want to say it loud?
The sound of pushing something onto the algol stack.
Okay, yes, pushing something on the algol stack, so go ahead, thunk. Okay, that's interesting. Whose claim was that one, do you know? Yes, I know, but I can't remember who it was, who was the person who said that. Okay, there's some, we looked it up somewhere. There wasn't Google then, you know.
The other one is that the thinking has already been done.
Yes, the thinking's already been done, it's been thunk. Right, okay, so this one takes three arguments, and so it's a three-argument up applicator. This one's what this does is the default just types out a known procedure type. But the handler for applying for strict procedures is the ones you just saw, except I'm evaluating the list here in the calling environment. Okay, and I have a handler for strict compound procedures, which does what it used to do, but it ignores the calling environment, doesn't it? No, it doesn't. It evaluates a list of operands, but the procedure environment is where it gets the extension from, the environment extension. Good. That's how I get lexical scoping. Okay? Okay? And of course, all the rest of these things are what I expect. Let me see where I'm going here. Yes. Okay, so that's the last thing. Okay, so now I want to add in non-strict procedures. Now I'm going to pick this. Non-strict procedures are things like things that are called by name or called by need or whatever. They're lazy evaluating objects. So for example, a good example is if, right? I mean, if really doesn't have to be defined as a procedure. It's actually non-strict in its first argument, but strict in one of the other two, and we don't know which until we have to evaluate it. It's an interesting object because really what if turns into, if, that'd be the real if of P consequent alternative is really the thing which says, which produces, this is either lambda of x, y, x applied to the consequent and the alternative, or lambda of x, y, y applied to the consequent and the alternative, non-strict. That is, it's one of these two. So it's the P is evaluating to one of these two, and we don't know which. This is therefore true, and this is therefore false. Lambda calculus true and false. For those of you who like lambda calculus, that's the sort of thing you may like. Okay. Okay, so here's the things we have to do. I'm going to make here a simple kind. And I'm not going to have some variables strict and some non-strict, but we can do that too. Okay, we can make it so you can mix the variables of various kinds. And you've got different kinds of declarations, like some are memo-wise and therefore what you call by need, and some of them are not. Okay, but those choices that we could add in. We can elaborate this thing as much as we like. It's fun. Okay? It's fun to make languages. Okay? But the thing, here's what you have. The handler for a valve for an N lambda is a non-strict computer compound procedure. Okay? In order to make if work, I have to force the value of the first of the predicate, because I can't make a decision unless I know what its value is. So this may come up with something like a promise or a thunk. I promise to compute something if I actually want to compute it, and sometimes I actually have to push, pull and get the value out. So that's what a force is. Okay, and we'll see that in a minute. I'll show you how you define those. Okay, and I have, in order to apply a procedure, I have to know what kind of procedure it is. So I better for a delayed object, if I have a delayed object I'm applying, okay, that's what the procedure is. First thing you do is force it and call apply again. Okay, I wanted to find out what kind of thing it is so that the applied procedure can in fact deal with strict ones, for example. There's a strict primitive procedure, which is going to take a procedure and operands in a calling environment and evaluate the list, forcing all the operands, because I need them. Where forcing the operands does the same thing as I saw before, except I'm forcing every operand individually. Okay? However, for non-strict procedures, it's different. For non-strict procedures, I'm going to apply them, I want to delay their operands. Okay? So that's I'm going to have the extended environment with the parameters of the procedure with a bunch of delayed operands. Okay, and I might want to choose how to play this, because I might want to turn this whole business here into some sort of conditional, which really is a generic operation, which is how do I deal with an operand, so that I can deal with the various kinds of operands, some of which are strict and some of which are not. But I don't want to build that here because I don't have enough space on the slides, basically. Okay, and delaying a list is nothing more than building the argument list by evaluating the operands, but instead of evaluating them here, I'm delaying them. But I have to keep the environment at the time, because later I may need to use it. If somebody asks me the value of this expression, I better be able to evaluate, so I better connect its environment up and to store it somewhere. So delay has to remember the environment. Yes, sir?
This environment here is mutable, right?
Mutable in the sense that I can do assignments to its variables, in which case I have Jensen's device. Remember Jensen's device? Oh my gosh, you could write all sorts of weird stuff in Algol 60. But it was a fun language. Actually, one of the most beautiful languages ever invented. Very sad that it got turned into things like Pascal and IC, other things like that, and then died. Yeah, Scheme was a descendant of Algol 60 and Lisp. Basically, it's some sort of interesting offspring. I don't know exactly how to say that.
Bastard child.
Bastard child, thank you. Okay, right. Now, what does it mean to force an object? What it means to force an object is say, if it's delayed, force its value. So that's going to go buzzing around until it comes up with an undelayed object. Okay? That's all. Yes, sir?
Breaks tether efficiency.
Yes. We'll worry about that later. Okay? That's the yes. Yes. And let's see, do I have anything else? Oh, no, where's delay itself? Come on, didn't I put delay in? Ah! Whoops, I think I left one thing out. Okay, well, all delay is a thing which, delay of a object, I can write it in many ways. Yes, delay of an object in an environment. If I could build a new object, which is called a delay, which is just the object and the environment, and then I have to have two parts: the delayed object and the delayed environment. Okay, and then I have to then what it means to force it. The bottommost force is going to be what does it do here? Oh, there. Oh, yeah. There it is. It's doing the right thing. Delayed expression environment. That's it. Okay, so I left out one thing. Well, that's actually it for today. I ran at approximately the right time. Okay. if there are questions, I have 5 minutes before the world comes to an end according to Google time. Are there questions about this material? Not even from Colorado, huh? Yes? Yes, sir, or ma'am.
What do you mean that
Oh.
is non-strict?
What I'm saying, the evaluation of no, if is non-strict. If is non-strict because some of it's because I don't have to know whether C or A is going to have a value before I finish the value of an if. So, for example,
Strict means what?
strict means that all of the arguments must be evaluated. Okay? So, for example, I'm sorry, I didn't mean to lose those words. Here. Yeah, but okay. Yes. Okay. Fine. Any other questions? Yes, sir.
Sorry to keep harping on mutability of environments.
Yes.
If you were to define a statement as returning positive,
Talk louder so everybody can hear you.
if you were to define a statement or one of these nodes is if a statement returns instead of a value environment pair, and then you define the define operator as returning an environment that has the old environment plus the new definition, doesn't that allow you to handle things like forcing of a delayed operation in the environment at the time
I think
it was
you're
created?
right. I'm not sure.
So
What you're
doesn't that
asking
make
for-
this
what you're-
more general?
What he's asking about, I think, is whether you pass around what's called a store. Okay, he's talking about one of the ways you can represent assignment and side effects in a side effect-free manner in a single process situation. If, however, you have, and that's true, but it has a real problem when extending it to multiple things, and I think the real... Yes, but let me see if I can. Let me explain something that's interesting here. Whether or not you have assignments is actually a point of view question. Okay, and it depends upon whether or not you're looking at this from a transcendental point of view or immanent as a deity. Every programmer is a deity in his computer. Okay, if you're part of this process, that is, you're talking to something and it's changing, you say it has independent local state. Okay, and that's true if you break your programs up into pieces. So each piece is talking to other pieces, and they see the other pieces changing. That's independent local state. That's a view. It has to do with being immanent, part of the system. If, however, it turns out that you stand outside the system and look at it from outside, it is perfectly possible to arrange it so there is no assignment. The way that works is that the state is being passed around through all of these things, but the parts are not seeing it. Okay? Now that works very well if you have only one process communicating. Okay? If you have multiple what are apparently independent processes, that is time is involved, okay? That you have the time becomes a partial order, okay? Then there actually is state, and you can't do anything about that. Okay? And there's a whole bunch of theorems about that. Okay, and that's what you're seeing. So you're seeing a picture of the way time exists. What assignment does is it installs a moment in time, because what it creates, in fact, the existence of assignment produces time. Okay? Oh, I'm sorry, yes?
So why do you need quote?
Why do you need it?
All of the other things that you defined in a circular interpreter were actually required in the interpreter itself. But there's
Oh,
no
yes, there
use
was.
of quote.
Yes, there is, but you didn't see it. Where it says how do I do the syntax? If the syntax for Lisp, okay, define self-evaluating. I can't write on this thing. This is not a chalkboard. It's awful. Come on. SELF, evaluating, question mark, of expression, okay? Okay? If this were Lisp, I would say not cond, I'll just say and pair of exp, is it a pair, and EQ,
You're thinking about quoted.
that's right. Oh, I'm sorry, I didn't mean self-value, I mean quoted. Sorry, you're absolutely right, quoted. Thank you, sir. Make it lambda. It's easier. Lambda. A lambda expression. Cont EQ, car of the expression, quote lambda. How do I have a symbolic constant if I don't have quote? Because otherwise I'm asking for the value of the symbol lambda. So I have to say this is the symbol I'm interested in rather than its value. Okay? So it was there, it's just what you. Well, it doesn't matter. I could have had strings, but then I don't have a lot of the flexibility I might want. Like for example.
You might want it to be some sort of a function that only returns true for certain requests.
Right. And the point is, if I choose to have strings there, then of course those strings can't be variables. Okay, which means I wouldn't be able to change the meanings of some things that I might want to be able to change. Although I don't want to change the meaning of lambda, I have to admit.
The real
Okay.
reason is if you don't put in quote, you can't do Lisp,
Yes.
right? Because you need the quote in order to talk about the structure.
Right.
If you leave it out, then you can do other kinds of languages that don't have that feature.
Yeah, but you have the
I
choice.
just wanted to call that out.
I know.
Yeah.
So-
That's why I answered it, because Jerry wasn't.
No, I was answering the question. He said it wasn't in the thing I wrote. I was saying yes, it was. He didn't see it.
Yes.
Okay, that's a different question I was answering.
That's right.
Okay, yes, right.
I want to make a comment here. Okay, so what Jerry just spent an hour talking about is a way of doing what we call language layering, where the layer is a fully opaque language. Okay, so you've totally isolated yourself from the next layer down. So you have the implementation layer, which in this case is Scheme, and you have the layer that you're building, which could be Scheme, it could be something else. It doesn't matter, but you're completely isolated from the underlying thing. What we're going to talk about tomorrow, and probably on and off for the rest of the week, is less isolated kinds of language building. You can build layers very easily that can be helpful, that are partial layers, that allow you to capture certain kinds of sublinguistic parts, let's say, that are helpful in building up nice abstractions. Okay? So that's the teaser to get you to come back tomorrow. Alexi.
So, why is this stuff great?
This stuff is great.
Or good at least?
Oh, well, I think that.
Oh, this is cute.
Besides fun, but I think the most important answer is that that having this good set of skills that I'm showing you here gives you ability to write your programs in such a way that you don't get yourself caught in corners.
Here's the real answer,
Okay.
okay? We'll go back. Greenspun's 10th law. Does anyone know what that is?
Oh yes,
Anyone? Raise your hand if you know what Greenspun's 10th law is. Okay, so hardly any of you know what that is. Greenspun's 10th law is that any sufficiently complicated program has a Lisp inside it somewhere. That's right. Well, yes, that's right.
right.
That's correct. And I'm not convinced I know how true that is, but the answer is that if you're in that position, now you know what to do. You can build yourself a Lisp very easily.
Is that to say that any alien civilization that programs long enough will invent Lisp?
I think it's just one of those typical egotistic quips that people like
Greenspun would write.
comes up with.
Yes. No, but certainly they have to.
This is a lot less useful than some of the other techniques
Sure.
we're going to come in talk about. On the other hand, there are times when it's appropriate to just build your own language. I mean, look at what Stallman did this for Emacs. It was clearly a win for him over the long run because he has this nice programmable layer that's very general and can be expanded. Okay, but that's not always what you want to do. Okay, you have to make sure that the people that you are talking to who will be using your system are capable of dealing with that. Okay? And, you know, not everyone's happy with that. On the other hand, there's now a lot more Lisp programs than there used to be because of Emacs Lisp. So.
Yeah, and there's also a little bit of truth to the Greenspun thing, which is if you're doing a sufficiently complicated symbolic manipulation like a compiler or anything like that, then somewhere along the line you're going to be inventing symbolic manipulation objects. Many of those are randomly organized, generally parse trees of some sort. Okay, parse trees of structures. Well, when you're in that world and you're going to build that stuff, damn it, that's what Lisp is. It's the general mechanism for moving around things like that in a very easy way. So he's saying that if you're going to build something like that, you're going to do it. Every compiler I've ever opened up has certainly had basically a Lisp, little, whether or not the author knew it, had built a little Lisp interpreter inside of it somewhere. Yeah.
Well, it's also true about Haskell and Prolog and so forth.
Not quite, and I'll answer why. The answer why it's not true. It's because the crucial thing about the Lisp is not the details of the fact that it's functional or anything like that. The crucial thing is that there's a simple representation of programs as data.
That's also true of Prolog.
That's true of Prolog, but it's not true of Haskell.
Correct.
Okay? I was responding to the thing you said, and.
Prolog has its own problems.
Yes, but they're different problems.
That's not it.
It doesn't have a quote and has a different eval operator.
And it has different, that's right. I said, of all the only language I excluded from the list that looked like this was Prolog,
It's okay. Every Lisp program has a Prolog interpreter in it, too.
of course. And vice versa.
And vice versa.
We have certainly written some.
Right, right. Mm-hmm.
It
Yes.
sounds like the mechanism for applying generics is very much like a Prolog interpreter.
Could be. This particular one isn't.
Yeah, well, I
This
besides
particular one is
that, it's a pile
ridiculously
of
simple.
cons.
Yeah, it's actually a bunch of, it's a ridiculously general search space.
Mm-hmm.
Oh, there we go. We're at Google. There we go.
Okay. So it's time to relax for the moment.
Yes. So-
I need some
Come
fluid.
back tomorrow.
Mm-hmm.
We'll talk about some more fun things. Completely different.
Yes.